Hello everyone. These are the exercises for the second week of MAT1362. We'll be doing exercises 1.31 on subtraction and then some from section 2.2. And these will just be quick solutions so that you can look these over. And if you have any questions about these solutions, feel free to ask in the DGDs this week. All right, so 1.31 is to prove the remaining parts of proposition 1.28. These are the exercises about subtraction. The first is to prove this statement. So, proof, we know, let's start with this. Let's consider. We know by the definition of subtraction that this is A plus the additive inverse of B, and this is C plus the additive inverse of D. Like this. Now, here we can regroup this. We want to get the A and the C together and the B and the D together. So what's the best way to do this? Let's do this. Yeah, so let's first associate these first brackets to get this. Now, let's swap these two with commutativity. A plus commutativity of addition. Now I'd like to use associativity on the brackets on the inside. And now we can associate these larger brackets to get A plus C together. This is again associativity of addition. Now here we're going to use proposition 1.24 part 1, which says that the additive inverse of D plus the additive inverse of B is the additive inverse of D plus B, which you should remember from last week. Like this. Now by definition, adding an additive inverse is subtraction. And I think now just this D and this B are out of order, so we can swap them back. With commutativity of addition. The second statement says that A minus B all subtract C minus D is this on the left. So we can begin our proof. Let's consider the right-hand side. We'll unpack this with the definition of subtraction. Like so. Check all our brackets. Now, here we'll apply proposition 1.241 again. And what we'll get is the additive inverse of C plus the additive inverse of the additive inverse of D. Now here we can say that the additive inverse of the additive inverse of D is just D. This is proposition 1.20 part 1. And now we just have to use associativity and commutativity to group the A and the D and the B and the C. So let's do that. with some associativity. Let's put the negative b and negative c together, also with associativity. I'm going to commute the two pieces inside the large brackets. Associate together the a plus d. We can apply 1.241 again here to get the additive inverse of b plus c. And now we're adding an additive inverse, which is, by definition, subtraction. Part 4 is an if and only if statement. It says a minus b is equal to c minus d if and only if a plus d is equal to b plus c. So rather than have a string of equations, or a string of expressions all equal to each other, justified by axioms, we'll have a string of equations, one implying the next, justified by axioms. So for our proof, let's consider the fact that a minus b is equal to c minus d. That's our assumption on this side. Now, this implies that we can unpack the definition of subtraction on each side and still have an equality. This is the definition of subtraction. Now we can add b to each side by replacement. The replacement here is that we know a plus negative b is equal to c plus negative d, so we're replacing a plus negative b with c plus negative d over here. Now there'll be some steps of associativity. Just on the left-hand side. And now negative b plus b is equal to 0. And this one is proposition 1.8. Then a plus 0 is equal to a by the additive identity. So all of these steps you can see have, in some sense, moved this additive inverse of b to the other side as a b. So what we'd like to do is the same thing with negative d. And to do this, we add d to both sides by replacement. I'm going to start writing over here to give myself some more room. So a plus d is equal to all of this over here. By replacement. Noticing how the brackets build up here to keep track of which order things were added. So now we have some associativity to work with, because we'd like to group together this negative d and this d. So let's commute here. First on the inside. Now we can group together this b and this c. associativity. And now we can move the large outer brackets. With associativity. Now here, again, we have negative d plus d. We know that's 0. And this is by the same proposition as up here, proposition 1.8. And then b plus c plus 0 is just b plus c by the additive identity. And so we've proved one direction. We started here with the left-hand equality, and we arrived at the right equality. Now, because this is if and only if, we have to go in reverse. We have to start with the right equality and arrive at the left. So consider that a plus d is equal to b plus c. It's going to be more or less the same steps, but in reverse. Whereas here, we first added a b and then added a d to both sides. We're now going to add a negative d to both sides and then add a negative b to both sides. So this implies a plus d plus the additive inverse of d is this by replacement. And we're going to work on this left-hand side. First, we'll use associativity to group together the d and additive inverse of d. Now, d plus negative d is 0. This one now is just the normal additive inverse identity, or additive inverse axiom. And a plus 0 is a by additive identity. Now we have to add an inverse of b to both sides. Which is another replacement. Replacing the a in this expression with what we know it's equal to from the previous equality. And on this side, we have to do some more rearranging to get together this b and this negative b. So we need to do some associativity and commutativity to get this b and negative b together. So let's first commute these two pieces inside these large brackets. By commutativity. Now let's commute the b and the c. Now we can reassociate to group together the negative d and the c. So we get a new bracket in here, plus c, plus b, one bracket here now because we've moved these around the c and the b. It's associativity, and we can apply associativity again now to move these outermost brackets around the b and the negative b. So we get this. By associativity. Now b plus negative b is 0. By additive inverse. And anything plus 0 is that original thing by additive identity. Now we're almost where we want. These brackets can be removed now because there's nothing else around. We just need to commute this negative d and this c. And now that we're adding additive inverses, this is by definition subtraction. And so we've gone the other way now, which completes the proof. The last part of this exercise is part 5. It's to prove that a minus b all times c is equal to ac minus bc. So to begin this proof, we will consider the left-hand side. And first, we'll use the definition of subtraction to write this as a sum of an additive inverse. Now, this c needs to be distributed. I'm going to use proposition 1.6 to distribute from the right. So this is ac plus the additive inverse of b times c by proposition 1.6. And this is equal to ac plus the additive inverse of b times c by proposition 1.24, part 3. Now we simply have an addition of an additive inverse, which we can write as a subtraction with the definition of subtraction. Completing the proof. Exercise 2.2.1 is to prove proposition 2.7. It's the proposition which tells us that n has no largest element. Formally stated, it says that for each natural number a, there exists a natural number b such that b is greater than a. So to prove this, we need to let a be a natural number. We just have to show that there exists such a natural number. So we can construct any such b we want with this property. We're going to recall proposition 2.4, which states that 1 is a natural number, and therefore a plus 1 is a natural number by closure of the naturals under addition. So this is going to be our b. So let b be equal to a plus 1, which is a natural number. Now b is greater than a if and only if b minus a is a natural number. So we can consider b minus a. b is a plus 1, so this is a plus 1 minus a, which is equal to 1, which we know is a natural number by proposition 2.4. So therefore, b is greater than a, and that completes the proof. For any natural number, we can construct a natural number b such that b is greater than a, so such a number exists. Exercise 2.2.2 is to prove the remaining parts of proposition 2.9, part 4 of which is in the notes. The proposition is about 4 integers, a, b, c, d, and the first part says that if a is less than b, then a plus c is less than b plus c. So proof. We get to assume everything that's part of the if statement. So let a, b, and c be in integers and assume a is less than b. What does this mean? Well, by definition, this means that b minus a is a natural number. By definition. All right. Now we would like to know whether b plus c is larger than a plus c. So we're going to consider b plus c minus a plus c. We're not making any claim about this yet because we don't know anything about it. We're just considering this integer. We can rearrange and say that this is equal to b minus a plus c minus c, where c minus c is 0. So this is just equal to b minus a. But we know that b minus a is a natural number. So therefore, because b minus a is equal to this first expression, b plus c minus a plus c is a natural number, which means that a plus c is less than b plus c. Part 2 states that if a is less than b and c is less than d, then a plus c is less than b plus d. So again, beginning our proof, we need 4 integers. Let a, b, c, and d be integers, and we can assume the if statement and assume that a is less than b and that c is less than d. We can unpack what this means. This means b minus a is a natural number, and c less than d means that d minus c is a natural number. Now we would like to know whether b plus d is larger than a plus c, so we can consider b plus d minus a plus c. Again, stating nothing about it, just considering this integer. We can rearrange this to be b minus a plus d minus c. And now we know that b minus a is natural and d minus c is natural, so their sum is natural. By the closure of the natural numbers under addition. So, since this number is natural and it's equal to b plus d minus a plus c, this means that b plus d minus a plus c is natural, which means, by definition, a plus c is less than b plus d. Completing the proof. Part 3 of this exercise is to prove that if 0 is less than a, which is less than b, and 0 is less than c, which is less than or equal to d, then we can say that a times c is less than b times d. Now, because less than or equal has 2 parts, either c is less than d or c is equal to d, we're going to do this in 2 parts. So case 1, we're going to let a, b, c, and d be integers and assume 0 is less than a is less than b, and that 0 is less than c is equal to d. So since c is equal to d, we can just use one symbol for each of them. It's just 2 different names for the same integer. Now we can unpack what this means. A is less than b means that b minus a is a natural number by definition. But also, c is less than 0 means that c minus 0, which is equal to c, is a natural number. So now we can multiply these two. This means that c times b minus a is natural by closure of the natural numbers under multiplication. And so we can distribute. This means that cb minus ca is natural. but C is equal to D. So we can replace C in one of these with D. And rearranging, it means that BD minus AC is natural, which means that AC is less than BD, which is what we wanted. In case 2, let A, B, C, D be integers, and assume that 0 is less than A is less than B, and now we assume that 0 is less than C is less than D. We're going to unpack a few things here. This implies that since B is greater than A, that B minus A is natural. Since D is larger than C, it means that D minus C is natural. Because inequality is transitive, this also means that B is greater than 0, which means B minus 0, which is equal to B, is natural. And here C is greater than 0, so C minus 0, which is just C, is natural. So now from all of these are all natural. We can multiply and add them in any way, and they'll still be natural numbers. So this implies that B times D minus C is natural, and that C times B minus A is natural by closure. And here we were using multiplication. Now we can add these. And it will still be natural by closure of the natural numbers under addition. And now this we would like to expand and rearrange. So this means that BD minus B times C plus C times B minus C times A is natural. BC and CB cancel out. So this means BD minus CA is natural, which I'm going to write as BD minus AC, just using commutativity. And this means that AC is less than BD by definition, as desired. Exercise 2.2.4 is to prove proposition 2.13, which states that if we have a natural number A and some integer B, and they satisfy the property that A times B is natural, then B must have been a natural number. So the proof for this is going to rely heavily on proposition 2.3. So first, let's get our assumptions. Let's let A be a natural number, B be an integer, and assume that A times B is natural. So we're going to use proposition 2.3 in a proof by contradiction. So by proposition 2.3, exactly one of the following is true. Where these are the statements that B is natural, the additive inverse of B is natural, or B is equal to 0. We would like to conclude that B is natural, and we will do that by showing that the additive inverse of B can't be natural, and that B itself can't be 0. So, case 1, assume towards a contradiction that the additive inverse of B is a natural number. Well, A is a natural number by assumption, so this means that A times the additive inverse of B is natural by closure. Under multiplication. But A times the additive inverse of B is just the additive inverse of AB. But if the additive inverse of AB is natural, this means that AB is not natural by proposition 2.3. It states that exactly one of the following are true for any integer. And so if the additive inverse of AB is natural, it means that AB is not natural and AB is not 0. But this is a contradiction because we've assumed that AB is natural. So this contradicts the fact that AB is natural by assumption. So therefore, our initial assumption that negative b is a natural number is wrong. So therefore, the additive inverse of b is not natural. So we've ruled out this possibility. Case 2. Let's assume towards a contradiction. That b is equal to 0. Well, then a times b is equal to a times 0, which we know is equal to 0. And 0 is not a natural number. Therefore, we've shown that a times b is not natural, but this is also a contradiction to the same assumption. It means that our assumption is wrong, so therefore, b is not equal to 0, which means if we go back up here, we've ruled out this possibility, and therefore proposition 2.3 states that the last possibility remaining must be the case. So hence, b is a natural number, completing the proof. Exercise 2.2.5 is to prove the remaining parts of proposition 2.14, with part 4 being in the notes. Part 1 says that if we have negative a is less than negative b, this is if and only if a is greater than b. So because this is an if and only if, we have to work in both directions. So proof. Let's let a and b be integers. Now in the forward direction, we're going to assume the left-hand side. So assume that negative a is less than negative b. By definition, this means that negative b minus negative a is a natural number. But we can do some rearranging here. This is the additive inverse of b, and if you subtract negative a, this is plus a. And so this is a minus b is a natural number. And if a minus b is natural, this means that a is greater than b by definition. So we've arrived at the right-hand side. To prove the other direction, we assume the right-hand side, and we work similarly back towards the left-hand side. So this means that a minus b is natural by definition. This means that we can write this as negative b plus a is natural, which we can write as negative b minus the additive inverse of a. So that is natural. And this means that negative b is greater than negative a by definition. And we were aiming for negative a is less than negative b, which is the same. So we arrive back. So we can go from one statement to the other, which means that they are equivalent, completing the proof. Part 2 is to prove that if c is greater than 0 and ac is less than bc, then we can conclude that a is less than b. This is going to use one of the results we just proved. So proof. Let's get our assumption set up. Let a, b, and c be integers, and assume that c is greater than 0 and AC is less than BC. We can unpack these with the definition. If C is greater than 0, it means that C minus 0, which is just C, is natural. And if AC is less than BC, it means that BC minus AC is natural. Now, since BC minus AC is natural, BC minus AC is equal to C times B minus A. This is factoring out the C and then doing some commuting, but you get to this. Now we just had a proposition which said that if a product is natural, and you know that one piece is natural, and we know that C is natural, then we can conclude that B minus A is natural. This is by proposition 2.13 that we just proved. So now that B minus A is natural, this implies by definition that A is less than B. Which is the conclusion we wanted. And this completes the proof. Part 3 is very similar, except now we're working with C less than 0. And if C is less than 0 and AC is less than BC, then B is less than A. So the inequality flips when you multiply by a negative number, is what this is proving. So, proof, let's begin the same way. A, B, and C be integers. Assume C is less than 0 and AC is less than BC. Let's unpack what this means. If C is less than 0, that means 0 minus C, which is equal to the additive inverse of C, is natural, and that BC minus AC is natural. Now, what we're going to do is take BC minus AC. We can write it as C times B minus A, as we did previously, but we can also write it as negative C times A minus B. And this is natural, because it's equal to BC minus AC, which we know is natural. And now again, we can apply proposition 2.13, because we know that a product of two numbers is natural, and we know that one of them is natural, negative C. So this implies that A minus B is natural by proposition 2.13, and this means that A is greater than B by definition, which is where we wanted to arrive, completing the proof. The last exercise, exercise 2.2.6, is to prove that if we have three integers, a, b, and c, where a is less than or equal to b and b is less than or equal to c, then a is less than or equal to c. This is similar to proposition 2.6, which states that strict inequality is transitive. Here we're proving that less than or equal to is transitive. Because less than or equal to means either strictly less or equal, there are some cases here. So we can have case 1, a is equal to b and b is equal to c. Case 2, a is strictly less than b, b is equal to c. Case 3, a is equal to b and b is strictly less than c. And case 4, strict inequalities on both. So if we can show that a is less than or equal to c in each of these cases, then we'll have a proof that holds always. So, proof. Let a, b, and c be integers and assume that a is less than or equal to b and b is less than or equal to c. Case 1, let's assume that a is equal to b and b is equal to c. Well then, this means that a is less than or equal to b by assumption. But we can just skip immediately to a is less than or equal to c, because b is equal to c. which is a proof in this case. Case 2 is essentially the same argument, because here we didn't use that A is equal to B. It just mattered that B was equal to C. So let's assume that A is strictly less than B and B is equal to C. Well, A is strictly less than B by assumption. This means that A is strictly less than C, since B is equal to C, but strictly less is included in less than or equal to. So we have our result in this case. For case 3, we assume A is equal to B and B is strictly less than C. So B is strictly less than C by assumption. This means that A is strictly less than C. Since A is equal to B, we can just replace it. And if something is strictly less, we have that it is less than or equal. And finally, in case 4, assume that A is strictly less than B and that B is strictly less than C. Together, these imply that A is strictly less than C by proposition 2.6, which states the transitivity of strict inequality. And once A is strictly less than C, it means it is less than or equal to C. So in every case, we arrive at A is less than or equal to C. So it holds in general, and that completes the proof.